I'm gonna be going over, this is gonna be a geometry lecture, but then it's also like only one tiny part of like geometry problems. It's a little bit hyper-focused, but this one tiny part keeps showing up, so let's do it. First, let's talk about dot products, right? So if you are familiar with dot products, a lot of times it's described as like kind of the similarity between two vectors, and specifically the dot product between two vectors x1, y1, and x2, y2 is going to be like the product of the corresponding dimensions added together. And if we visually, let's visually look at kind of an implication of this. If we have a specific direction vector that we want to dot something with, well, you can kind of think of if we have a specific point that's going to be dotted with this vector, and when I say a point and a vector, they're kind of the same thing, right? Since it's like a point is a vector from spanning the origin to that point. This point dotted with this given direction vector has some result, right? And it has some x value and it has some y value. If we wanted to move the x value to a different point, right? If we wanted to shift the x value, there's going to be some corresponding y value, right? That will have the same dot product result as it, right? And if we are shifting the x over by some amount, right? Like kind of going further in this direction, assuming like kind of without loss of generality, the vector is pointing in this quadrant, right? We're going to have to shift the y down a little to make up for it. And if we plot this kind of downwards amount that we have to shift by, and you like algebraically kind of prove this, right? If we consider some result that we want from the dot product, all of the vectors that have this result are going to lie on the perpendicular line to that direction vector, right? And if we want to have a higher dot product, then it's equivalent. The frontier is basically just moving further along in this direction vector. But if you want 2 points to have the same result, they're going to be on that line, right? Such that the intersection point is like the kind of point that has that given result you're looking for. Does that make sense to everybody? Right? And so that's cool. Now we're gonna kind of use this to solve a problem real quick. Excuse me. And that's a really good way of visualizing kind of dot products and how they like just a good way of visualizing the results of dot products. So what we're going to do is we're going to consider a problem called bribing Eve. We're not actually going to consider the full problem, more just the generalized form of it that cuts away a lot of the crap. There's a lot of like tie-breaking stuff and like only worrying about one quadrant that I don't really care about for this lecture. So we're going to consider the kind of generalized form of you have a bunch of kind of food items, and they have some parameter, let's say, like size and like quantity and tastiness, right? And you're going to judge each of these food items. Each different judge has like a different value, right? Like maybe if you're particularly picky, you might assign a score of like 99 to tastiness, but like 5 to size of like how much food you're getting, right? So a judge will assign some like ranking metric that they will have, right? That they will pick these two parameters, and then they will, to judge each food item, then they will take the corresponding size and tastiness values multiplied by their parameter that they've chosen and calculate a score, right? And we'll score all the items. Now, Eve, assuming if I remember the flavor text correctly, has one of the items in this list, I think the first one, right? And she wants to know if she can bribe the judges, or the judge, I guess, it's one judge, in some way. Oh, I guess Eve is probably the judge. If we can bribe Eve to change, so this is like Carol or someone, the protagonist of this story. If we want to bribe the judge to change their parameters to be anything that we want it to be, right? How high in the ranking can we be, right? How good can our meal be if we were to score them and rank our meals? Does that make sense? Like, how good can we make our meal relative to everybody else's meal, assuming we have full control over the judge parameters? So, how I've described this, I think it should be fairly clear in this dot product-esque lecture that the operation I'm describing, the scoring operation I'm describing, is a dot product, right? So we're trying to find, if we consider we have a bunch of, if we plot all these meals, right, as points on the plane, we're trying to say if we can pick a direction vector, right, and we have some special point, what is the direction vector that we can pick if we, well, we're not looking for the direction vector, but if we pick the optimal direction vector, how good can we have the ranking, where the ranking is like basically your relative position if you were to sort all these points along the direction vector. Does that make sense? And so we have a fixed special point, right? So as we've kind of described, when we're dealing with dot products and we have some direction vector, you can kind of think of like all points having the same dot product with that vector as a perpendicular line kind of sweeping across the field, right? So if we consider like all the different direction vectors that we could pick, all of these direction vectors are as if a line is sweeping across this field, starting from the outside in some direction, right? And what we'll notice is that the point that we actually, like, we care about, like, if this is our direction vector that we've chosen, right, or sorry, this is the perpendicular to our direction vector, right, yeah, that's just going to be annoying. We care that when it crosses Eve's line, right? Because if it's facing this direction, then, like, if this is going this direction, then we can say everything to this side of the line is better than Eve, and everything to the opposite side, like kind of, I don't know, left and right, kind of like a little bit weird. I'm not going to use those terminologies right now, but it is going to be worse, right? And so what we notice is that we kind of, like, despite it sort of, at least conceptually, the way I'm conceptualizing it, approaching from the outside, we only care about it when it crosses Eve, right? So we can consider Eve to be the center point, and we can, like, sort of rotate this perpendicular to the direction vector around Eve, and you know, once we deal with all the tie-breaking stuff that is like actually in the problem, we will see that, like, what the problem actually is like, what's the best way to have some line going through this point such that, like, the number of points on one side of that line is, like, minimized, right? Does that make sense? And so we can do this with sort of like a radial sweep where you sort all the points around Eve, and like a lot of times, like, for implementation details, you might want to, like, duplicate the points to make it like easier to implement, like mirror the points, and like there's some problem specifics where, like, really you're only allowed to choose like positive direction vectors and all that, but like that's not really, I'm not really focusing on the radial sweep aspect of this, right? Like, this is a fairly standard radial sweep that, like, while annoying to implement, is like at least hopefully conceptually sound. And I would recommend solving this problem if you have not done many radial sweeps. But does everybody understand the solution to this in theory? Yes.
I don't understand why the vector that we choose for like the judge or whatever has to go through Eve's thing whenever like the whole parallel line is, or the whole like perpendicular line that intersects with Eve's. So like, could it be optimal to like put it like somewhere else?
This is a direction vector. This doesn't have a position, right? So when we choose our direction vector for like how we're our judge vector for how we're scoring these points, right? One, like, the magnitude of the judge vector doesn't actually matter, right? Because like we can say the judge vector is like the unit vector of the judge vector scored by that and then multiplied by its actual scale, right? So the judge vector is just a direction. And so let's say we picked a judge vector direction that forms this parallel sweeping line, right? Where we're saying, okay, everything on this line has the same score, right? And we're like moving this line across. Well, when we intersect with Eve, which we're only going to do one time, everything before it is a worse score. Everything after it is a better score, right? And what I'm saying is that if we hypothetically like did this, right? We sweeped a vector like this, we sweeped a vector like this, we sweeped a vector like this. Whenever we're doing that computation is going to be when Eve, like when we're deciding the results of this is when the vector is exactly on Eve, and that's when we're going to check, okay, how many points are better, how many points are worse. And so that's a functionally equivalent to actually just rotating the line around Eve instead.
Okay.
Does that make sense?
Yeah.
Any other questions? Okay, and so that's how you solve, at least like without loss of generality, how you solve bribing Eve. Yeah. So that's cool. Now let's consider bribing Eve 2, a made-up problem that I've decided to make up. And in bribing Eve 2, we're no longer bribing Eve. We've changed our ways, and we are just managing the competition. So what we have is a list of meals that all the contestants have made, right? Let's say like 10 to the 5th meals. And what we're now doing is we're going to have like a line of judges each give us their scoring parameters, right? And we will decide, not decide, there's no decision to be made, but we will tell them which meal won according to that judge's scoring parameter, right? So we have like 10 to the 5th meals in this list. And like there will be 10 to the 5th judges, right? And so like flavor text kind of be gone, right? We have 10 to the 5th points, and we're doing 10 to the 5th queries of like sort of direction vectors. And for each direction vector query, we want to what's it called? Find the best scoring meal, right? You can even do this as like LR queries, like instead of a full list. You know what? Sure, we'll do it as LR queries. So we only care about like an LR range of meals, right? I guess the LR queries will just come at the end. You'll see why you can do it with LR queries pretty clearly after I explain how to solve it. So we have some points, right? And we're trying to say, okay, if we have some given direction vector, what is the maximum? What's the maximum point in this direction, right? So you know we're gonna visualize it how I've kind of been describing, and we're sweeping this line across. And what I hope is like a little bit intuitive is that if we draw the convex hull, of these points, right, the best answer can only ever lie on, for now we'll say the best answer can only ever lie on the perimeter of the convex hull, right? And the reason why we can say this is because, you know, like kind of only an intuition, is like, let's just say, yeah, this is the best answer, right? Well, if this is the best answer, that's inside the convex hull, if we kind of draw that line, it's either intersecting the convex hull, in which case there has to be more convex hull on the other side, or it's on the edge of the convex hull, in which case you've proven my point. The answer's on the convex hull perimeter, right? So the best point to be like dot producted with is going to be on the perimeter of the convex hull. Now, how do we actually find it, right? Well, what we can consider is sort of and actually I'll even say this, it's going to be one of the points on the convex hull, not like some arbitrary point that's like on this edge, right? Because that point doesn't actually exist on the data, right? Because if we're intersecting a line perfectly, then both of these endpoints have the same magnitude, so you can pick them. You don't have to pick something in the middle that you might have gotten rid of when you were making the convex hull, right? Does that make sense? Okay, so we know it's a point on the convex hull. Now, how do we find it, and how do we find it fast? Well, we can consider another property of convex hulls, which is, this isn't necessarily true how you have it returned from like when you call the convex hull function, but we can say is that like, while the points are what's returned, these edge angles in a convex hull, right? There's some rotation of them that is sorted by angle, right? You could theoretically like it's kind of like what's it called? Like adjacent edges in the convex hull will be monotonic, except for the fact that when it's returned, it could be split at like a bad area. Like you could like, it's kind of like I think there's like a classic LeetCode problem of like find the rotation of the array that's sorted. There's going to be some rotation of the convex hull that these edges are sorted by angle, right? Does that make sense? And the only reason I have to specify that it's some rotation is not like, this isn't some property of the convex hull, it's just like how we are representing it as a list of points given back to us, right? So there's some rotation of the convex hull that all of these edges are sorted by angle. Does that make sense? Yes.
When you say a rotation, you mean a rotation of like the array of points?
Yes, I should have specified. A rotation of the array of points and the corresponding edges that array like represents, right? You can rotate that array in some way such that all the edges will actually be in sorted order. Sound good? Cool. And so we can go back to our frontier that we're pushing, right? And we can say is that this frontier is actually the last point that this frontier intersects on the convex hull is going to be the point, like like it's either going to be like the edge that its angle is exactly the sorted angle of this edge, right? So like if we're pushing a frontier like this, it's going to be like perfect, or it's going to be the point where the two edges connecting it, my sorted angle is between their sorted angle, right? And it can only be like one point that's true if you're not the edge, right? And so that is like a monotonic binary searchable function. So you can actually like binary search this. it sucks, right? It sucks a little bit to like actually implement this. Every time that I've used this in the problem, I've actually used, I think it's called like extreme vertex in Cactal, because in the line hole intersection code, there is just some sub-function in Cactal called extreme vertex that does this exact thing, where given a convex hole, given a direction vector, like find a extreme vertex, and there could be like two. And so yeah, but that's like conceptually how it works, right? It's like when you have these convex hole edges sorted by angle, right? This is now like a function that you can binary search on, and you don't actually have to fix the rotation when passing it into extreme vertex. Like it just does it like kind of finds the split point and does it for you. In like only in a conceptual way. Implementation details for that are to be damned. And so yeah, so that's how we could answer like for a given list of points. Like let's do direction like maximum point in this direction queries, right? And then if we want to do LR queries, you can just, instead of making it one convex hole, you can just have a segment tree of convex holes and query each full cover node with the extreme vertex. It's not that deep. But, well, it is a little bit deep because you have to kind of you kind of have to use like a merge sort tree argument to say that in each full cover node, that's not power of 2, whatever. In each full cover node of a segment tree, this example is way too damn big. In each full cover node of a segment tree that you're building on these points, right? If you were to have each convex hole represent all of the points in the range, each point is only in log nodes. So the sum of the sizes of all those convex holes is like n log n, and so you can just like build all those convex holes in the full cover nodes, and you'll be fine. You won't run into any runtime concerns. So then it would be like n log squared, because then for each full cover node you can do your extreme vertex binary search and take the best answer out of all of them. And so that's bribing Eve 2, problem I just made up. Any questions on that? Cool. So then let's get into. I was going to go over like a world finals problem, but I think a better that kind of is a similar thing. But then I found literally 2 days ago by coincidence a problem on Caddis that I like better. So this problem, how's my time going? I'm at like 27 minutes, looks like.
Yep. 11:29.
Oh, okay, I can't read a clock.
That class also.
Okay, so in this problem, you have some points. Who would have thought the geometry-ish, well, not ish, it is a geometry lecture. The geometry lecture has a bunch of problems with points. You have a bunch of points on the plane, right, like 10 to the 5th of them, and what you want to do is you want to make a fence around these points, right? Specifically, you want a rectangular fence. So you want to place some rectangle in the plane so that it contains all these points. It does not have to be axis aligned. Oh, I should tell you what you're trying to do. You're trying to find a rectangle that has minimum perimeter. So you want the minimum perimeter rectangle that can contain all of the points in this plane. It does not have to be axis aligned, because if it had to be axis aligned, like, come on guys, you can do this. It'd just be like min x, max x, min y, max y, like do the math. And you want to place the minimum perimeter rectangle such that it contains all these points. Any questions about what the problem is? Let's say 10 to the 5th points, coordinates up to 10 to the 9th. Yeah. Cool. Does anybody want to make a hazardous guess or some observations or some anything?
Do you always want one of the edges to be on the wall?
You do. It's relevant, and I'm not proving it in the lecture. Random guess that we're gonna make is that it is always optimal, right? Like non-strictly optimal, I guess. To have one of the edges of the rectangle flush. Well, okay, actually, first thing we should say. Sorry, I guess maybe we all did this, but the equivalent problem is to wrap the convex hole with a rectangle, right? Because no rectangle that you can make can ever push into the convex hole, right? So if we only had the points on the convex hole, we would have the same answer. And we're gonna say we want to contain this convex hole of points with a rectangle. And then the observation, and so that one is like that's just true. And then this is more of like a slightly difficult to prove, and by slightly difficult I mean like I spent 5 minutes trying and I couldn't quite work out anything clean, so I'm not doing it in the lecture. That one of the edges of this bounding rectangle that we want will be parallel to, will be flush, I should say, with an edge of the convex hole, right? Okay, now that we have that, does the solution pop out to anybody?
Can you just go through every side and do the extreme vertex?
Okay, the extreme vertex. What is the extreme vertex?
That's perpendicular to
So you're saying get like this one?
like for each side of it.
Yeah. So then what the problem? So then it actually ends up being fairly easy, right? Is once we have an edge, we consider one edge as like this is going to be an edge that's in that's part of our rectangle, right? And if we're trying to minimize the perimeter, right? Well, we're trying to minimize kind of two almost disjoint parts of this perimeter, right? We're trying to minimize like this length, right? And we're trying to minimize like this height, right? So if we're trying to minimally wrap the polygon, right, and we know our rectangle is flush with this, then the minimal height, right, is going to be whatever point is like the furthest away that we have to take. So it's going to be whatever the maximal point is in this perpendicular direction, right? We have to like bound it there, right? And then there's going to be the minimal point. Now we have to kind of get the rectangle sides, right? So we need the minimal point in this, in the direction, like arbitrarily the direction of the edge and the reverse direction of the edge, right? And like for this flushed edge, this is going to be the minimal perimeter rectangle that is produced like kind of by this edge, right? By this edge, because we've kind of independently minimized now every part of the perimeter, right? Does that make sense? Is that intuitively, is there any gut instinct feelings on incorrectness of this, or like why is this true, or is my explanation sufficient? Cool. And so then, since we have the magic function, we can do this in like just n log n. What's up? Since we have the magic function, we can go through each edge, find it in the directions, get the points, like do the math, right? You have to like actually get the actual dot product and call it a day. Let's say the bounds were like 5 times 10 to the 6 or whatever, right? So that we can't like use our magic function. Well, what we could do is like as we move this point around, right? like what we can do is we can get an edge, right? Have our three like directions that we're trying to independently maximize, right? Find the starting points for each of those directions from this starting edge. As we move this edge around, these directions will all be like monotonic in how they move around. So you can have like a couple 2-pointers going to do everything in linear time if you hate it yourself. Does that make sense? Like the fact that we can 2-pointer this if you really, really wanted to. Just like these are all independent problems that we're solving, and so as we move this edge around, like the corresponding point that we're looking for is only ever going to move around in like sort of the same direction. So it's like it's 2-pointerable. What's up?
You don't even need a 2-pointer, because, well, I guess that has a log, though. Never mind, don't.
Well, now I want to hear it. Like, do you have like a different log?
So, essentially, a very important property of extreme vertex is that, like, the extreme vertex is always going to change when you, like, if you, like, do it, like sweeping on, like, radial direction, the extreme vertex is always going to change when your direction vector lines up with a side of the polygon. Like you're going to move your extreme vertex based off of that.
With the normal of the side.
Yes, normal of the side.
Yeah, so, okay, so what I think Ty was saying is like if you have each of these edges, right, and you get like your extreme vertexes, right, and like you, or sorry, not extreme vertex, you have like your sort of like direction vectors that are produced. Let's just say we're trying to find like the opposite guy, right, without loss of generality, we're only trying to find one thing. What's gonna happen is that what you can do, right, I guess you kind of have to like turn it back into the parallel line, but what's gonna happen is like if you were to sort this interleaved array of like the convex hole points and the, not convex hole points, like the convex hole edges, and these lines produced by these extreme vertices, then they're all gonna be between like the guys, right? Is that kind of what you're saying? Like implementation details might be a bit different.
Don't
but,
quite understand what you're trying to say. Like what I'm saying is that like consider this rightmost point on the polygon. That's going to become the extreme vertex when you're like, if you radially sweep counterclockwise, that becomes the extreme vertex when your direction hits the perpendicular of the side before that.
Yeah, we're saying the same thing. This will be the extreme this, I guess some
It's
edge.
intuitive to draw the outward normals.
I was gonna say, like, that's why I'm trying to, like,
If you intersect that half plane with that one, there's some area where that will be the extreme vertex.
Yeah. So then if we like actually if we put like all the extreme vertexes like in a list, they would be like when in sorted order between these two vectors.
Yeah.
Yeah.
I like have like a kind of weird to think about proof for like why it's on an edge,
Sure.
which is like the resulting function, like if you assume that like you know your 4 points that are on like the rectangle, like if you draw a rectangle so that there are like 4 points and only 4 points on the outside, then you can like the function for like if you turn like the rectangle, what the perimeter is like the sum of two like sinusoidal functions. And so if you take the derivative of that, the only time that you're at a local minimum is when like the angles were like perfectly like misaligned, and that will never happen. So you can always tilt your rectangle in some direction to make it better until they're now like, and when like the function changes is when you hit an edge. So it's like a little convoluted.
Yeah, it's okay.
I think you can also look at like a triangle inequality with like if you rotate, you have to use like the hypotenuse between those 2 points instead of like the.
Yeah, it like for me at least, it's like it feels very similar in the vibes to like I don't know the problem I'm trying to think. Like all those problems where you can always move it a little until you get to like some local minimum.
I think it's
Yeah,
easier to
but the
first
proof
look
here
at
is
the
what-
case of like rotating calipers of like diameter,
Mhm.
realize why the diameter is optimal, and then you can extend that to the rectangle case.
Ooh, that's kind of nice. Okay. Anyways, yeah. We don't do proofs here. Everything is rhymes. That's a joke. Is it? So, okay. Next problem. Let's get into the computational geometry graphics minds, right? Hey, can anyone tell me if these two convex polygons intersect?
Yes.
Okay, so human error should be avoided, and so we need to do this with computers, right? And so we need a computational way to avoid certain human error, right? And so this is the problem that we're doing. We want to know if two convex polygons intersect, and I will say for this problem, touching at a point is intersecting, since I guess you have to define that, I guess. So yeah, how can we do this? And how the hell is this extreme vertex? So there is a theorem called SAT, called the separating axis. Why did I erase the polygon? Okay, there's a theorem called the separating axis theorem that says if two convex polygons don't intersect, there is some axis or some edge where we can draw an infinite line, like kind of flush with that edge, such that like the polygons don't cross that line, right? Like strictly cross that line. Does that make sense?
I don't think the theorem actually says it has to be flush, but then you can move it to be flush.
Yeah. So that might be true. I've always just used it as flush because you can always move it to be flush.
Yeah.
And so what this means is that if we wanted to have a fairly easy to implement way of checking convex polygon intersection, I might have messed up the equality case when I said this. This might be strictly not intersect. I'm sorry, I didn't actually resolve this before the lecture. I'll figure out the details after, but we can consider like if it solves strictly not intersect, then you could still check strict intersection afterwards fairly easily with like a point online check, a point in like a non-strict point in polygon check. Which, by the way, you know, I just want to point out to anybody who's saying like, can I just check for one polygon if like any point of one polygon is inside the other? No, like no, break case, cross case. So using the separating axis theorem, what this means is now if we just kind of brute force the separating axis, then we can go through every edge of both polygons, and basically for this line, right? If we pick the direction vector that's pointing into the polygon, and then query the other polygon for the point that is most in that direction, then if at some point we like find a point who is like kind of strictly on the one side, then we have found a separating axis, and the convex polygons don't intersect, right? If that never ends up being true for any of the things we query, then the polygons do intersect, right? And then of course, in contest, I'm going to use extreme vertex, right? Because I highly doubt the bounds are going to kill me for the log factor. But if you wanted to, you could again do this as like a 2-pointer. because you can always do it as a 2-pointer. I'm like never gonna do it as a 2-pointer because like the 10-line book code go burr. But like it's like always 2-pointerable if you want to. Except when it isn't. Don't quote me. And so that's like a fairly like easy application. And like there's a bunch of 2-pointers that like you don't need separating access theorem that you could do to like actually like you could probably like you could ternary search, or there's like a bunch of ways you could solve this, but I find this to be like a fairly easy and clean method to do this. Does anybody have any questions about that? Don't interrogate me on the strictness of the separating access theorem. I'll have to double check that after the lecture.
You can get the, like, if they do touch, like, there's a 1 or 2, like, extreme vertices on that line, and you can do line segment intersection.
Yeah. So like either way, it's fine to solve it, but I just like forgot that detail.
Yeah.
Of like the actual trueness. And so I'll have to double check that after the lecture. Okay. Yeah. So that's a fairly easy application. And then the last problem I'm gonna go over is a problem I wrote for the OSAJEC competitive programming camp called Stepping Stones. And let's see if I have, yeah. So in this problem, you're gonna answer queries, which first of all, what you're given in this problem is up to 10 to the 5th polygons, 10 to the 5th convex polygons, I should say, with points, I think, up to like 10 to the 6. The bounds are a little funky because I made the bounds a little bit smaller than they necessarily need to be to prevent a bunch of like overflow, annoyance. But you have like 10 to the 5th polygons where the sum of points are bounded, and they're like in an array, right? And what we're going to do is we're going to answer queries, which are if I have some river that I want to cross that is defined by 2 parallel lines, right? And I want to use some subset of these polygons that's defined by like a continuous LR range. Is it possible to cross the river with these polygons? And what I mean by cross the river with these polygons is there some way to translate, because these polygons don't like, their actual position is irrelevant, right? Is there some way to translate the polygons such that like we can like cross the river, right? The polygons can overlap, they can overlap with the banks. Touching exactly is enough to like to walk across it, right? Like if we have like 2 triangles, right? This exact vertex point, like as long as we have some path that can cross over, we're good, right? So we want to know, using this LR range of polygons, convex polygons, I should say, can we get from one bank of the river to the other? Each query is also like a different river. So the river has like it's defined by 2 parallel lines, so some rivers might be wider, they might be going in different directions, the LR range changes between queries, and there's like 10 to the 5th of them. Okay, so far so good. Any questions about the problem? What's up?
Sorry, did you say that you can rotate, or was it only
No,
rotate?
you cannot rotate,
Okay.
because if you could rotate, you would
Just
like
the longest.
yeah, you would get the what's it called, the polygon diameter. Is it diameter? Is it called?
Diameter.
Yeah, you get the diameter of every polygon, and then it would be like a segment
Yeah.
tree query on the sum. So it wouldn't be awesome.
I was gonna say.
Okay, yeah, no, you cannot rotate. It would be a much easier problem if you could rotate, because if you could rotate, like I said, diameter, it would just be a segment tree query on the sum. Okay. Does anybody who has like not solved the problem before, does anybody who this problem is new to them have any progress on it whatsoever?
to get like the functional like progress that a shape makes, so to speak, like the vertex that it adds to your, or like the vector that like adds to your path, you can use extreme vertex thing with from the line of like the left bank to get like the vertex. It's like from 0 to that point is like what that polygon effectively does.
Yes, perfect. I'm gonna modify that a little bit. I think you're right, but what each in a given direction. So first of all, this bank that we have, right? The location of the bank is irrelevant, right? What we're really trying to do is we have some direction vector, which is the perpendicular vector to the river, right? And we basically want to know, can we glue these polygons together such that they contribute like enough towards the direction, towards this vector, right, to cross the bank. The actual position of the bank is relevant, right? And what we can say is that in each direction vector, each polygon has some contribution, right? And so like we can notice that we have like a polygon like this, right? Its contribution in this direction is a lot larger than its contribution might be in this direction, right? And so, and we can say that the contribution vector that each polygon produces is going to be actually the like extreme vertex going in like arbitrarily one direction of the perpendicular to the river, like the difference in the extreme vertex going in the two different directions, right? The two different perpendicular directions. And so that means that we have, if we have these 2 points, we have the vector contribution of this polygon, and that would be really cool, right? And so that's like enough to basically solve this for one query, right? Is we can find the direction vector of this river, get the extreme vertexes in that direction vector, in the opposite direction vector, get that vector contribution for the polygon, sum those up, and then since we like don't really want to do dot product or like have any sort of floating points or whatever, what we could actually literally do is take one of the points on one bank, get this vector, right, and just check if it ends up being on the other side, right? Like you don't actually need to get the scale of the actual dot product. You can work strictly with the vector themselves. That is the difference between the two extreme vertexes, right? So that solves one query. And so now to solve multiple queries, there's 2 solutions. I think I'll go over the easier one conceptually. So what we can do is, as we've kind of talked a lot, like building up to this, these direction vectors, right? They if I were to query just what's the extremal point, right, in a given direction vector, as we go from one extremal point to the other, right? The vector, the actual extremal point will like change, right? So what we could do is, and like one solution to this is if we sort all of the queries, right? What we can kind of do is we can sort all the queries, and then also, and I'm kind of only speaking in like a conceptual way. How you choose to implement this is up to you. But you can sort all the queries, and you can sort all of the kind of like edge directions of the polygons, and you can like find, like as you are radially sweeping, and you're not really doing a sweep, you're sort of like doing an adjustment, as you're going from one direction vector to the next, right? There's going to be some polygons where they will like shift to the next point, right? Like where the extremal point changes, and like if you have all of the sorted edges, you kind of know which polygon that's gonna which polygons that will affect. And so as you like sweep through all these direction vectors and kind of keep track of like what's the extremal point in every direction, which by the way, since we're technically getting like the contribution going in two different directions, as long as we can answer these queries, right, then we can just treat each query as like, we can answer just two queries and like and combine them, right? Like if we can answer like what's the sum of direction vectors, what's the sum of like extremal points in that direction, then we can subtract the sum of extremal points in the other direction. And so then what that means is like you could build a segment tree on like these vectors, and then as you go and process through the queries in sorted order, you keep the segment tree up to date, and then you query the LR range of the segment tree, and that will give you like your total contribution to see if you can cross the river. And like you're basically like this is like one of those things where like kind of now you have to do the 2-pointer, but you don't necessarily have to do the 2-pointer. My original solution to this, since I have like 3 more minutes and it's not too much to talk about, was if you know about Minkowski sums, 30-second Minkowski sum. A Minkowski sum is if we have two polygons, if we consider like all of if we basically take, okay, this is the polygon. If we take one polygon and we sort of like move it around the other and get that corresponding shape, right? That's not how you do it. How do you
Keep it on one point, like don't move it off the point. No.
I can't.
Keep it on one point and don't change the point.
Like
You will erase it by the fact they're using an eraser.
Okay, let me give the actual definition since this sucks, and I can't physically do this for some reason. Like do I even have enough time for this? Not really.
No.
Okay, I think that's it. I think if anybody wants to hear the other solution after, basically you Minkowski sum the polygons, you make a merge throw tree out of them, and then it ends up becoming the contribution of extreme vertex for each Minkowski sum polygon in the full cover nodes of the segment tree of that LR range.
I would also like to point out that the first solution we forced because the Minkowski sum solution requires an extra log factor.
It doesn't. Like
It 100% does.
well, no, like you can build the tree without the log factor, and you can do the query like with the 2-pointer if you wanted to.
Oh, that's fair. Okay, never mind.
Like yeah, so the easy implementation is unlog squared, but you
more-
could do that solution without the log factor.
What I'm more so saying is you made a comment earlier of like not needing a 2-pointer, you can just like always slam extreme vertex, but this is an example where like that could be.
Yeah, if you up the bounds, you could like make it so that you have to do the 2-pointer. But
Not to quote him.
yeah, don't quote me on that. And then you quoted me on that.